First of all, I'd like to thank the organizers for inviting me. My main affiliation is actually in Germany nowadays, but we are in the German-Chinese Research Center, eventually. But this research, in particular, is mainly associated with IIASA. As one of the pillars of IIASA research is on equity. We recently published a paper with Brickman on how research heterogeneity can facilitate cooperation. We get a number of blog spots and tweets afterwards, which kind of highlighted these papers. Okay, capitalists still like it, because now wealth inequality is such a great thing. So, in essence, I don't want to talk about this. Okay? No. I would like to talk about something that actually research heterogeneity actually hinders cooperation. And we will see that both of the results can be, we have both of these in our model. So let's start with a kind of an introduction. We all know the public domain. We all start our introduction in game theoretical papers that yes, the basic prisoner's dilemma or public good game has an ESS as just defection. And this is a very symmetric, homogeneous game. We usually assume that it's a well-mixed population. All individuals have the same roles. They are on some regular random graphs or even geometric. And what are other symmetries in this game? Once we change this very symmetric, homogeneous game, cooperation usually is more easy to obtain. Like if we assume that they are on some, there are some local interactions, for example, space, or there's a role asymmetry, as in the famous book by Smith, 80%. Or you have heterogeneous distribution of connections, or if you introduce punishment. All this changed the game by introducing some kind of asymmetry. And in this talk, I would like to introduce yet another asymmetry, wealth inequality. That individuals might have different resources to themselves. So let's say there's just two kind of sides, so to speak, or research, rich and poor. The rich are R1 and the poor are R2. And this is just it looks complicated, but it's just a basic public good game for two individuals. So the cooperative doesn't invest everything, so it doesn't retain anything for itself. It invests whatever resources it have, and when they pull it together, they just split among themselves. Okay? So if two rich cooperators meet, they don't retain anything for themselves, but they pool their resource, both of them investing R1, then they split, and after multiplication, they just split. Okay? This is the public good game we all know. But because we have rich and poor individuals, the payoff matrix is not just 2 by 2, but 4 by 4. Actually, we have 4 parameters here, but if you normalize and make some changes to this payoff matrix, it becomes quite simple just having 2 parameters, B and C, where B is the temptation to defect. If it's high, there's a high temptation to defect. If it's low, there's a lower temptation to defect. And C, which is just a contrast between the rich and the poor individuals. The game itself is a very normal spatial game. The players interact in a regular graph. They can either be in a rich or a poor side. They can either cooperate, which means they invest all their resources into the public good game, or they defect, and in that case we don't invest at all. And then we update their strategy based on the payoffs they get by playing with their neighbors. And the update is asynchronous and proportional to the payoffs, to the chance that they update their strategy. Yeah. What do we get? Just to see what I'm showing. Let's say we start from a population with 50-50 of cooperators and defectors. In the homogeneous case, we have just, let's assume just poor individuals. Okay, in the homogeneous case, it doesn't matter. It can be just rich or just poor, but it doesn't matter. So 50% are cooperators, the blue one, the red ones are defectors. And if the temptation to defect is high, not surprisingly what we get is just defection. If the temptation to defect is low, what we get is just cooperation. Okay? This was shown like maybe 20 years ago. If we introduce this heterogeneity, that certain individuals are actually rich, is the ones with the more vivid color. Like this is a rich cooperator, this is a rich defector. And what we get, when temptation to defect is high, we still get cooperators in equilibrium. We still stay in the population. There's a coexistence of cooperators and defectors. Even though in a homogeneous environment, defection would be the norm. Okay? Conservatively, what we get in a low temptation situation, in which, in a homogeneous case, there will be just cooperation, we get defectors in that population. Defectors still remain in this population, even though in a homogeneous population, they will go extinct. So, this is just a larger parameter space. Basically, there's always a kind of peak of cooperation if we introduce research heterogeneity in case of high temptation to defect, and there's a dip in the level of cooperation if we introduce heterogeneity, when otherwise there would be full cooperation. And the severity of this changes with contrast. If you have a higher contrast, a high difference between the poor and the rich individual, then either the increase in cooperation or the decrease in cooperation is actually larger, shown by this kind of a valley. The valley itself is broader if we increase contrast. Contrast is increased in this, in the y-axis. Okay? Contrast is increasing, and the level of cooperation increases, or the level of cooperation actually decreases. Yeah, there's a decrease. Okay, so again, in a homogeneous setting, in this case, there will be full cooperation, and in the heterogeneous case, there is less cooperation, considerably less cooperation, 40% opposed to 100%. And in the high temptation case, we get like 20% cooperation instead of just no cooperation at all. Well, these results are quite robust. We tried very hard to make the model different, to break it. So the update rule can be changed to synchronous or deterministic. We increased the neighborhood size from 4 to 8. We introduced other graph topologies. We know that the regular lattice is a very artificial topology. But when we introduce, for example, a scale-free graph, which is reminiscent of some network in real social settings, true for animals, also true for humans, we still get the same result. Okay, the very kind of same figure like this one can be shown. Okay, exactly like this one. We also introduce strategy executions, but cooperators sometimes make errors and they just defect. It doesn't change the result. We also made, in this we had just two, in the basic model, there was just rich and poor individuals. But we can introduce a bit of continuous resource space, just bimodality, that more richer individuals and more poor individuals, and it doesn't change the system. If we go for an n-player game instead of just a 2-player game, the same result still holds. Okay? So this is very robust. At the very heart of this result there's a peculiar special configuration of this good and bad, it's rich and poor individuals. What we did in order to understand our system is to measure what kind of local configurations are prevalent, they have a high abundance, and what are kind of surprising. Surprising means that if I would just randomly throw out good and bad sides and cooperators and defectors, I will get certain configurations. But instead of what I usually observe is different. Okay, and the surprise factor was how these kind of configurations. These are configurations which are very common in equilibrium. Equilibrium we have in a stochastic simulation, and they also deviate from the mean field frequency. I would like to kind of note this and this configuration with a rich individual in the middle and poor ones at neighboring this. It's actually true for nearly. Oh, sorry. Wrong. So in nearly all of this configuration, what we see is there's one rich individual somewhere surrounded by poor ones. And if you do a fundamental cluster analysis, introduced by someone who's here, then we know that in the homogeneous case, this block of cooperators can grow if the temptation of the defect is lower than 1.25. Okay? And actually, at this regime, this block of defectors can collapse. Okay, which means that if temptation to defect is smaller than 1.25, you get full cooperation. If it's higher, you get full defection. This is for the homogeneous case. Now, when we introduce heterogeneity, then, for example, this block of rich cooperators in a sea of poor defectors can grow if B is smaller than 1.25 times C plus 1. Which means that even if B is larger than 1.25, we can have a certain C value at which this inequality can be satisfied. Which means that this block of cooperators can even grow if B is larger than 1.5, which would be the kind of the threshold in a homogeneous setting. The same is true that this block of defectors usually collapse in a homogeneous case, but if even if B is smaller than 1.25, at which it should actually collapse, there is a certain, if we increase the contrast, we can get into a parameter space when this particular configuration cannot collapse. So this kind of proves that there is a different outcome for homogeneous resource distribution as opposed to heterogeneous resource distribution. And it's all and this result increases with contrast, as we have seen in the simulations. Actually, I think that for this particular case, the fundamental cluster is not the 2x2 blocks, but this 2x1 blocks, which in the homogeneous case can never grow, can never be collapsed. I mean, this is the homogeneous cluster, just two poor cooperators among defectors. This can never grow in a homogeneous case, no matter what. But this can actually, if it's heterogeneous, it can actually grow, given enough contrast. Okay, and this is a homogeneous configuration of just two local defectors. It can never be collapsed in a homogeneous case, but it can collapse, can be eliminated, even high enough contrast. Okay. So far I've shown results for a non-evolving, non-evolving in the sense that the trait, that there were either full cooperators or full defectors. Also, we have started from 50-50% of cooperators and defectors. And one might say that it's artificial. We have cooperation in the beginning. Was the surprise that we have cooperation in the end? So we introduced the evolutionary game, and there were a trait, propensity to cooperate, which is just the probability that a given individual play a cooperator. And we start with full defection. Okay, the population is at full defection. And still what we observe is that, well, let me show you the next one. There's just two more things to introduce. The trait can either be fully unconditional, meaning that the site quality doesn't affect the trait, or individuals can play differently based on what resource they have. So for example, richer people can be more cooperative than poorer ones. So it'll be a nice outcome, which we didn't get. So in a fully unconditional case, we get pretty similar outcome, or non-evolving. Non-evolving in the sense of a non-continuous trait. Okay, so even for zero, if we start from zero cooperation slowly kind of builds up and can reach full cooperation when it should actually reach full cooperation. So it's another kind of robustness check. The interesting result is that if we have conditional cooperation, first of all, the dip itself, the increase in cooperation at high temperature is actually much larger. It affects a larger parameter space. So if individuals can base their decision on what they have, what kind of resource they have, then the outcome is that even more cooperation, even at the greater parameter space, is possible. Well, the dip itself is also a bit more prevalent. And what we usually see is that it is the poor individuals who carry the day. Very similar to what George was showing us like 20 minutes ago. So it seems that it's the poor ones who cooperate more, and the whole system is becoming more and more cooperative in the end. Now, if I want to kind of compare our results to what we've seen in history, then we can identify a number of transitions. In the animal world, equity is not really prevalent. Definitely not in the chimpanzee world, for example. Or in ancestors, probably, we don't know, of course. But at least chimpanzees live in a very hierarchical society. They fight an awful lot among themselves for power. But early humans, and which is seen still in hunter-gatherers, contemporary hunter-gatherers, are very kind of for equity, so to speak. Okay, they reverse inequity. They don't like being different in wealth-wise, what they have for themselves. So there was a transition from kind of the animal world, which is mostly characterized by hierarchy and wealth inequality, to humans, which has a more equal society. Then there were again two other transitions. One of them we experienced when there was a transition to agriculture. Our human society again became very hierarchical. Think about the pharaohs. Some of them had huge tombs. The rest of the population were just slaves. Okay? But fortunately, I think there's another transition going on nowadays. Equity is on the rise. Well, hopefully it will remain so. If you want to understand these changes, at least these ones, all results might add to this picture. Because what we got that wealth inequality hinders cooperation and efficiency of producing the public good is high. I usually said temptation to defect. But temptation to defect is just the inverse of this R. R is the parameter of how efficient is the production of public good. If it's high, then the pooled resource has a high return. Okay? So if this return is high, so we are very good at producing public goods, then wealth inequality is not a good thing anymore. If it is low, it's actually worth to be inequality. So we might say that in ancient societies, when producing this public good, in a very new setting, I mean, from hunter-gatherers, these early ancient civilizations, with no urban societies, huge populations, maybe their production of public good was not very efficient. They needed this wealth equality in order to maintain their cooperative behavior, so to speak, so that their civilization can be maintained. But nowadays, that the production of public good is actually much better. We are in a more efficient society. We might actually transition back to a more equal society. And with that, I'd like to thank you very much for your attention.
This question.
Thank you very much. I have just a quick question, because you're talking about the poor and rich players. I was thinking of wealth distribution on Earth, and there we have a very strong gradient, let's say from the north to the south. And it seems to me that your results are very dependent on the distribution of the rich countries. So I was wondering, what would happen if you have some, let's say, a gradient, or if you just have the top 20% of your grid being rich countries and the bottom part being poor countries to reflect kind of the wealth distribution on Earth. Could you still see the effects that you were talking about?
Well, we are not modeling countries, but individuals. But still, if I just go back here, the effect is actually strong when there is very few rich individuals. I think I might skip that explanation. We have on the x-axis the fraction of rich sites, which means the fraction of rich individuals. And when it is pretty low, like 20%, we have the highest effect, either increase or decrease. If there are pretty much everyone is rich, there's not too much effect anymore. But in this, the more realistic setting, there is.
Thank you.
So, does this mean equity among the poor? Because, the whole political speech is equity among the rich.
Really? Yeah, I do. But,
that's how you win elections. Everybody's going to be rich.
But in the end, if everyone is the same, it doesn't matter if everyone is poor, everyone is rich, it's just a perception. But if you take that, the production of public good is great.
But you like these different results if everybody's rich or everybody's poor, or most people are poor. Did I understand it wrong?
Yeah. If everyone is rich, or nearly close to everyone is rich, then everything is fine. There's not much difference. But if you have more poor, which is more common, then there's this effect.
Thank you. Another question?
Thank you for a wonderful talk. I have a quick question. What if homophily, for example, George introduced, is introduced into a model? What happens?
I don't know. I mean, we have not simulated this. Even though I think that it will definitely have an effect, because at its stance, from this kind of fundamental cluster analysis, it seems that the poor ones have to imitate the rich ones. Because the rich cooperators by being rich and by being able to shoulder the cost of cooperation, they set a kind of role models to imitate. So that's actually important. So you might see a bit of decrease in the effect.
Yeah, I guess so. Because the reason why I asked that question is because you showed that the common and a major cluster in your simulation is that you know, a rich cooperator is surrounded by poor cooperators. So probably that and the heterophilic effect, you know, poor cooperator, poor person imitating a rich person is should be quite important in the model.
Yeah, you should do it.
Yeah. Nice question, Hisashi. I just think that the conditional evolution results that Adam shows go some way in answering your question, because there we allowed the poor to have a different strategy, a different probability of cooperating than the rich, and they evolve within the poor population as opposed to the trait of cooperating which evolves within the rich population. So I think we could, maybe with some caution, interpret that as perfect homophily. And then it works even better. Yeah? So I think that's an encouraging result.
Thank you so much, I understand.
Thank you very much. So nice presentation. My question is that your model is so spatial structure is fixed, right?
Yes.
And so assuming if each side is moving like us, so I assume each side is, for example, one individual, and so in that case the resource can be viewed as our human resource. Okay.
Yes.
And for example, we could be different in the sense of quality of genetics. So someone could be very clever from his birth, and someone could be not so clever because of handicap. In that case, could you any comments on some implication from your results?
Well, there's two ways to answer this question. One of them is why you don't have inheritance of the resource. And the answer to this is even if only the rich individuals would actually propagate, it would not mean that everyone will be rich. Even if, let's say, even in the animal world, what we see is that the alpha individuals usually have much more progeny than the lower ranking ones. It doesn't mean that all of their offspring are going to be alpha males. Only a small proportion of them. So in this sense, even if the good genes itself are inherited, wrong does not. Not in this one-to-one sense. So I think that, or assumption that the resource they're not inherited is fine from the biological point of view. The other part of your question is why don't we have mixing, at least some kind of a mixing in our population. Mixing, as for us, I know I have some papers on it, have a deleterious effect on cooperation. But random mixing, and this is only true for random mixing, is not very common in nature. Individuals don't go about randomly. They have strong preferences to some individuals. And when we introduce these preferences, cooperations again can be salvaged. So it doesn't really, it should not really change your result. Should not. I'm cautious. Without actually calculating that, you'll be 100% sure. And this is my hunch.
Okay, thank you very much.